What is stimulated Brillouin scattering, SBS? Have you ever wondered how light can interact with sound? This fascinating process is known as stimulated Brillouin scattering, or SBS for short. It occurs when intense light meets acoustic waves in a medium, often in optical fibers or other clear materials. When this happens, the light, referred to as the pump beam, scatters backward with a slightly lower frequency. This scattering creates a new light wave called the Stokes wave and generates an acoustic phonon, which is a quantized sound wave in the material. The magic of this process lies in energy and momentum conservation. The incident photon loses energy to create the phonon, while the scattered photon has its frequency shifted down by an amount that corresponds to the frequency of the acoustic wave. Typically, this frequency shift falls within the range of tens of gigahertz, depending on the specific material and the wavelength of the light being used. For SBS to occur, the light must have a narrow spectral width and high intensity, which helps it become stimulated rather than just spontaneously scattered. To understand SBS better, consider how it works. The optical field creates density variations in the medium through a phenomenon known as electrostriction. These variations then propagate as acoustic waves, which scatter the light. When the intensity of the incident light exceeds a certain threshold, the scattered light is amplified exponentially. This creates a strong backward propagating wave, which is a defining feature of stimulated scattering. This is different from spontaneous Brillouin scattering, which is much weaker. In the realm of emerging computing technologies, SBS holds several important applications. For instance, it plays a role in optical signal processing. SBS can help create narrow line-width fiber lasers and amplifiers, which are essential for high-precision sensing and communication systems. The narrow line width enhances signal coherence and minimizes noise. Another exciting application of SBS is slow light generation. This means that the group velocity of light pulses is significantly reduced. This effect can be utilized in optical buffering and delay lines, which are vital for managing data flow and synchronization in optical computing and communication networks. SBS also finds its place in optical sensing. Sensors that utilize SBS can detect changes in the environment, such as temperature and pressure. This capability makes SBS useful for distributed sensing in structural health monitoring and other applications that requiring precise measurements. While SBS has many beneficial uses, it can also present challenges in high-power fiber optic systems. It can cause unwanted backscattering, limiting the maximum power that can be transmitted without distortion or noise. Therefore, managing SBS is essential in designing optical communication systems and emerging photonic devices. In the context of nonlinear frequency conversion and optical computing, SBS represents a key nonlinear interaction. It can be engineered to manipulate light signals in innovative ways. By controlling light propagation through acoustic interactions, SBS provides pathways for developing advanced optical components that surpass traditional electronic processing speeds and bandwidth limitations. This fascinating interplay between light and sound opens up new possibilities in the world of technology.